So yes, students, let's start the class now. And what we are going to start now? EMI. Okay. So today's class we have to finish this. However time it takes, we have to finish it. Okay. Now let's see. So electromagnetic induction. We start with magnetic flux. Magnetic flux is very similar to what electric flux was. What was electric flux? Electric flux was dot product of electric field strength and area vector, or number of electric lines that are passing through unit area. We call them as electric flux. So here, number of magnetic lines passing through a unit area is magnetic flux, right? And magnetic flux is what? Dot product of magnetic field strength and area vector. Unit of magnetic flux, Weber. Unit is Weber. That means magnetic field's another unit is Weber per meter square. Okay. So far we have seen that Tesla. Now it is one more unit is there, which is Weber per meter square. Okay. The unit of magnetic field is Weber per meter square. Right. Then, do we want to know that what is its dimension also? Yes, definitely we want to know what the dimensions of phi is. Okay. So, magnetic field and area vector. Area vector we don't have any problem. It's L square. What is magnetic field's dimensions? From where we found it? We found it from force. So, what formula we saw? F equal to QVB. Or you can have F equal to BIL also. Okay. So, BIL if you want to have, that also is fine. Okay. So, BIL. Okay. So, its dimension is what? M, L, T minus 2. B as it is, I is A, and L is L only. That's length. Okay. So, what we have? M, T to the power minus 2, A to the power minus 1. This is magnetic field's dimensions. Okay, now we are going to put it over here so that we can find flux dimensions. So, flux dimensions are, this is M, T minus 2, A minus 1. Now, area means L square. So, here it is. These are the dimensions of flux. M, T to the power minus 2, A to the power minus 1 into L square. Okay. Alright. Then, what is important in this EMI? We want to know what is change in magnetic flux. Okay, there is change in magnetic flux happening. If suppose you bring magnet closer to the coil, so the magnetic field linked with the coil increases, or if you take the magnet away from the coil, magnetic field linked with the coil decreases. So there is change in magnetic flux happening. And with change in magnetic flux, according to Faraday's law, there is induced EMF in the coil. Okay, if there is change in magnetic flux, there is change in magnetic flux through the coil. Then EMF is induced in the coil. Okay, now question is why it induces. The reason for that is if you are going to change anything, then there is always an opposition. Like if a body is there which is at rest, when you want to suddenly move it, it opposes. That's what we call as inertia. Right? Same way here you want to change the flux, then there is opposition. Okay, there is opposition. So in opposition, what the coil or what the coil, yes, what the coil wants to do, it wants to oppose the change. What is the change happening? Maybe you are increasing the magnetic field through the coil. So what it tries to do, it wants to decrease it. Okay, it wants to decrease it. So in opposition, it produces its own magnetic field, which is opposite to the magnetic field that you are trying to increase. Okay, that's opposition. So here I'll write induced EMF is opposition of coil to the change in magnetic field through it. Change in magnetic field through it. Change in magnetic field through it. Okay, and this is what? This is what Faraday's law is also. This is only Faraday's law. But there is one more law, which we call as Lenz law. What Lenz law is? Lenz law gives us direction of induced current. Okay. And Lenz law clearly says that this process of EMF induction is basically based on conservation of energy. Based on conservation of energy. So I am writing over here induction of EMF in a coil is based on conservation of energy. Conservation of energy. Okay, how it is, I'll tell you. But induction of EMF in coil is based on conservation of energy. And what Lenz law says? It gives us direction of induced current. It says if loop is closed or coil is closed, if loop is closed, then direction of induced current is such that it opposes the cause of its induction. Opposes the cause of its induction. Okay, clearly same thing which we have written there. It's opposition basically. Okay, so induced current's direction is such that it opposes the cause of its induction. What is the cause of its induction? Change in magnetic flux. So it opposes change in magnetic flux. Okay, and alright. Now how can we say that it's based on conservation of energy? So see, very simple thing is there. If suppose we have one coil, this is a coil, and we take one magnet. Here is one magnet. And suppose this magnet is thrown towards this one. It's thrown towards this one with speed u. So what's happening? As it's coming closer to this coil, its magnetic field, because we know that its magnetic field is there, right? How is its magnetic field? Suppose this is north and this is south, and its magnetic field or magnetic lines, we can make like this. Okay. Like this. More we can make. Okay. So now what is happening? It's coming closer and closer. So earlier there are no magnetic lines linked with it. Suddenly, with this one, magnetic lines will come in contact with it. So that means magnetic flux changed. So in this one, EMF will induce. And since it's a closed loop, current will also induce. Okay. Once this current is induced in this one, once current is there, once current is induced, there will be energy in it. It will become a magnet. We know that whenever there is a current in the coil, it will behave as a magnet. True. But once current is induced, it will store energy. It will have energy. It will have energy. Which energy? Now, I can tell you it right now. That energy is called half Li square. What energy is there? Half Li square is there. From where it came? Now what has happened? As it's coming closer, okay, as this magnet is coming closer, its velocity keeps on decreasing. Okay, maybe when it reaches over here, when this magnet, okay, comes closer like this, okay, then what will happen? Its velocity has become v, and v is less than u. Okay, so I can say that if it's kinetic energy, we are going to talk. Okay, there is loss in kinetic energy, and this loss in kinetic energy is what? Half Li square. Okay, so if initial energy associated with the magnet, initial energy, if I say is half mu square, and final energy is half mv square, that is the kinetic energy with magnet, and if you add half Li square, both are equal. So initial energy associated with the system equal to final energy associated with the system. And that's what Faraday's law or Lenz's law says, that this process is based on conservation of energy. It's not that something else has come into that. It has taken the energy from this one because this is opposing it. Okay, what this is doing, it's opposing. So if we talk in terms of magnet, how it can oppose? This also has become magnet, and this end of this coil has become north and this end has become south. That's why it is able to oppose this magnet, approaching magnet towards it. This is able to oppose this magnet which is approaching towards it. Okay, so this is how we can prove that this is based on conservation of energy. Okay, alright, let's do a few questions on this one. So flux is 3t square plus 2t, then find EMF induced at t equal to 1 second. Very simple question. Okay, but first thing is, what is EMF? We didn't discuss about EMF at all. Okay, we said that if there is change in magnetic flux through the coil, then EMF is induced in the coil. So what is EMF first? EMF actually is negative of d phi by dt. Negative of d phi by dt. If the flux increases, then it becomes negative. If flux decreases, it is positive. What is the meaning of that? If flux is increasing, this is trying to decrease it. If flux is decreasing, this will try to increase. That is the meaning of minus and plus, right? Okay, so let's do this now. So here is phi given 3t square plus 2t, and he is asking E. So E is what? Minus d phi by dt. Very simple question. So 3t square means 6t and plus 2t means 2. So minus 6t plus 2, let's place t equal to 1 in that. So minus 6 plus 2, that is minus 4 volt. Unit of EMF, we all know that is volt. So minus 4 volt. Simple. Okay. Then what says next one? Next one, what's happening? In the previous question, if you see, flux directly was given to you that it is changing. Okay. In this one, magnetic field is given constant. It is 6 Tesla, and area is increasing. Okay, area is expanding. Okay, no problem. Why? Because flux is B dot A. Okay, so flux is B A cos theta. Okay, flux can change if we are just changing magnetic field. So then we can write it as dB by dt into A cos theta. If just magnetic field is changed, then also we can get the flux change d phi by dt, or we can get d phi by dt even only area is changing, dA by dt into cos theta, or we can get EMF when only theta is changing. That's also fine. D by dt of cos theta. So any of the three factors, if you are changing, whether you are changing magnetic field, you are changing area, or you are changing theta, in all the three cases, we are going to get the change in flux. Okay, so here what we are doing? Here we are changing area. Okay, no issues. So E equal to minus d phi by dt equal to B. B is as it is. This is what we are doing right now. Okay. Now what about theta? Theta here is not given. That means theta must be considered as such that cos theta's value is 1. That's why it's not given. Okay. So now what we will do here? B into dA by dt. So B into dA by dt. B is 6, dA by dt is 4t plus 4. T value is 2 seconds. 6, 4 into 2 plus 4. How much is this? This is 12. 12 into 6, 72. 72 volt is our answer. Right? Simple. Then next is in this one again magnetic field is given constant, but radius is changing. That means a coil is there, a coil is placed in magnetic field and its radius keeps on changing. So if radius keeps on changing means is the magnetic flux through that coil is changing, right? We can make it like this. If suppose this is the coil here and this is in the magnetic field. Magnetic field also we can make something bigger like this. In this is the zone in which magnetic field is there. Okay, maybe magnetic field is like this inside. Now what is happening? Area of this is changing. Whose area is changing? This coil, or its radius is changing in fact. Okay, what happened? Not getting selected. Oh, so I have to make it again. Okay, fine. So if its area is changing or its radius is changing, now earlier this is here, now it's this. So what you will see that now area involved with this one is more as compared to this. So as the radius is increasing, flux linked with the coil is also changing. Okay. Alright. So here we are doing d phi by dt. So E is d phi by dt. And here what we will write? B into dA by dt only, because area only is changing. And what is area? Area is pi r square. So d by dt of pi r square. Now pi is again constant. Who's changing? R. So B into pi into r square. R square's differentiation means 2r dr by dt. 2r dr by dt. Okay. Put the value. Magnetic field is 2. This is pi. Again one more 2 into r. R at 1 second. How much is that? 4. So 4. Then dr by dt. Now what is dr by dt? Let's see. So r is equal to 4t square. So dr by dt is what? 8t. Dr by dt is 8t. So at t equal to 1 second, at t equal to 1 second, this 8t is equal to 8. Dr by dt is equal to 8. So let's place it here. This is 8. So what's coming? 8 into 2, 16, 16 into 8, 128. So 128 pi volt. Okay. So in this way, whether magnetic field is changing or area is changing or radius is changing, we can find out what is the change in flux per unit time and we can find EMF induced easily, right? Okay. Loop in magnetic field. Okay. Before that, we'll solve few more questions on that one. What questions you want to solve? See. Common questions, you can find them in books. It says that if there is a coil like this, okay, and there is a magnet is like this, right, and it's falling. This is north, let's say this is south, and this is falling down freely with acceleration g. It's falling down with acceleration g. As it's approaching this coil, what will be the acceleration? The answer will be less than g. Okay, acceleration of magnet will be less than g. Why? As coil opposes the magnet. Okay, because of induction, opposes the magnet. Okay, then what happens? Next instant, the same coil. Okay, same coil is here now, and the magnet also. This magnet is now like this. It's going out. And this is north and this is south. It's going out. Now what is its acceleration? Its acceleration is A or its acceleration is less than A? Oh, sorry, G. It's A, which is G or less than G or more than G. Answer is this A is also less than. Here also we said that its acceleration is less than G, and here also we are saying it's less than G. Now what is happening? Now suddenly the magnetic flux of this magnet through this coil is decreasing. Why? Because it's going away. Okay, so when it decreases, again there is EMF induced. And what EMF induced will do? It will oppose the change in flux. So it will try to attract it. Here what it's trying to do? It's trying to oppose it. So here is north end and here is south end of coil magnet. Whereas in this case, here it wants to attract it. So this is north end and this is south end of coil magnet. This is how it arranges itself. Okay, here it's trying to oppose the same magnet, here it's trying to attract the same magnet. In both the cases, acceleration is less than g. This is opposition. Okay, so remember that in this case also and in this case also. In both the cases, coil magnet opposes the approaching magnet as well as receding magnet. Right? Okay, let's move ahead then. Okay, so here we are. In this one, what's happening? Loop is there which is entering in magnetic field. Okay, so if magnetic field, if we can have here, this is the zone of magnetic field. Okay, and we have taken magnetic field is into this loop, and this zone is inside, and this loop here is entering. Okay, so as it's entering, you can see that the area of this loop in the magnetic field is increasing. Okay, area of the magnetic loop in this magnetic field is increasing as it's coming towards it. And here we have taken V is constant. So at a constant rate, its area is changing. Now if I assume that this length, this here is A, okay, and is entering with V, then this length is going to increase with Vt every time because it's going to move Vt. Correct or not? Right. So Vt with which this is increasing. So area is increasing at the rate of dA by dt is actually A into V. Area is what? A into Vt. If suppose that initially it was 0 inside this one. So how? It's increasing every with time AVT. Correct. So dA by dt will be what? AV. Right. If I say magnetic flux is actually V into area. Or if I say d phi by dt, you will say B into dA by dt, which is A into V. So you see that this d phi by dt is also constant. D phi by dt is constant. Okay, but I have to make two graphs over here. One graph is for phi. What is phi? Phi is B into area, and area is what? AVT. What is area? A into VT. Okay, with every second, this is increasing. First it is V, then 2V, then 3V, then 4V, then 5V, like that. Till entire area is not inside. Once its entire area is inside, then flux is maximum. Okay, then flux is maximum. So we will make it over here. Okay, flux is maximum. Now how much is this length? Entire length we can write. Okay, then this is going to move out. Then what will happen? Then area decreases. So when area decreases, that time also flux is changing. Yes. That time also EMF will induce. Yes. So we have to make a graph. On a graph also, they can ask us questions. So that's why graph. So flux first. Now flux, you can see that B is constant here, A is constant here, V is constant here. We can say flux is proportional to T. So how it will be? It will be like this. The flux increases with time. Okay, then it's fully inside. Once it's fully inside, that means it becomes constant. Okay, then starts decreasing. Then it starts decreasing. Will the rate will be same? Obviously, rate will be same because velocity is constant. So it will decrease in this way. Okay, it will decrease in this way. Now here flux is maximum. What is that? VAV. The rate at which increases, the rate at which is decreased is constant. Okay. Now let's talk about EMF. What is EMF? EMF is minus d phi by dt. That means initially when it was coming inside, flux was increasing. So EMF will be negative. So here is EMF. And it will be constant up to this time. Okay, it's constant. Wait, we'll take help of this. So it's constant, right? Okay. Then what? After that, flux became constant. So flux became constant means EMF 0. No EMF. Okay. Then again here flux started decreasing. So if flux started decreasing means EMF positive. Okay. EMF will become positive. Okay, fine. So make it positive somewhere here. Okay. It's like this. Then between also if you want to fill it, we can. Okay. Like this we can fill, and then here also we can fill it this way. This is the graph. This is EMF negative here, this is EMF positive. Alright. Right. This is the graph. So remember that on the graph also they can ask you question. This represents what? Increase in flux. Rate is constant, means EMF is constant. Same way here. Okay. Right. Few more questions are there on this one. Let's see what we can do. So here question says R equal to 10 ohm. That means resistance is given. Okay. Resistance of coil. Initial flux is given to you 10 Weber. Final flux is given 50 Weber. So change is happening in 2 seconds. Find charge flown through circuit. Okay. Charge flown, how to find? Till now we know that E is equal to d phi by dt. Or negative d phi by dt. Now E is their EMF. So if suppose they are saying about resistance and they are talking about charge flown, that means definitely there is current flown in that. And if current is there, then I can write E is equal to I into R. Right. So I will be, value will be 1 by R minus 1 by R d phi by dt. No doubt about that. Okay. But he wants charge. So this current I can write as dq by dt. So dq by dt equal to minus 1 by R d phi by dt. So dq equal to what then? Dq equal to minus 1 by R d phi, or delta q equal to minus 1 by R delta phi. This is delta q. So we can find it. Now what is given to us? This resistance is 10. Okay. So 1 by 10. Delta phi is phi f minus phi I final minus initial. So 50 minus 1 by 10. 50 minus 10. So 50 minus 10. 50 minus 10. Not 40. 50 minus 10. So 50 minus 10 is 40. 40 by 10 is 4. So answer is coming minus 4. But minus we don't have to do anything with the charge. It is one charge flown. So for us it is delta Q is equal to 4. That's our answer. So here like this we can find out how much charge is flowing because of change in flux in a particular time. Okay, then let's see what this question says. A coil have 500 square loops, each of size 10, which are placed in perpendicular magnetic field, which increases at the rate of 2 Tesla per second. Find EMF induced. A coil has 500 square loops. So if flux is changing, it will be changing through all 500 loops. Okay. Fine. Side is 10 and magnetic field is changing. Okay, fine. So we will say that flux is basically N B A. Okay. And EMF will be d phi by dt or minus d phi by dt. So minus N into A into dB by dt, because here area is not changing, here magnetic field is. Okay. Then what? Let's put the value. This is 500. Area is what? 10 centimeters square. 10 centimeters. Each side is 10 centimeters. So area is 100 centimeters square. So 100 into 10 to the power minus 4. Okay. It's a square loop of side 10. Okay. So this is 10 and this is also 10. So area is what? 100 centimeters square. So we have written it 100 centimeters square. We converted into meter. Okay. So this become 100 into 10 to the power minus 4 meters square. Then dB by dt, which is 2. So 2. Okay. What's coming then? 500 into 2000. Okay. So minus 1000 into 100 into 10 to the power minus 4. So 1, 2, 3, 4, and this is cancelled. Our answer is minus 10 volt. Minus 10 volt. Okay. So all this, the questions we did so far were all on EMF induced, because of change in magnetic field it may be, because of change in area it may be, because of change in velocity or not velocity, because of some loop is approaching towards it, then what will be EMF, that all we found so far. Okay. Now we are moving towards self-inductance. Now what self-inductance actually is? The self-inductance actually means is, if suppose there is a coil and there is a current I in this one. Okay, its radius is R. If there is current in this one and this current is changing. Okay, I increases or I decreases, whatever. So if I is increasing, we know that magnetic field through the center, magnetic field at the center of this coil is mu naught I by 2R. We already know that. So if I is changing, magnetic field is also changing. And if magnetic field is changing, flux is changing. Okay. What is flux here? In this case, A into dP by dt. So magnetic flux is changing means EMF will induce, right? D phi, sorry, this is d phi by d. So E is equal to minus d phi by d. So EMF is getting induced. So what EMF tries to do? EMF tries to make induced current in that, and what induced current will do? It will oppose the increase in this one. That means induced current will be coming opposite to that. This induced current will try to decrease its value. Why? Because it's increasing. So it will oppose it. So this process is called self-inductance, because of change in the flux through the coil by the current flowing in it results into self-inductance process in the coil. Okay, and what is self-induced current is doing, or induced current is trying to do? It is trying to decrease the very current because of which it is induced. Exactly same thing like Lenz's law. The induced currents try to or opposes the cause of its induction. So this induced current is coming because this is increasing. So this induced current is trying to decrease this increase in this current only. Okay. So this process is called self-inductance, and this L is coefficient of self-inductance. What is L here? Coefficient of self-inductance. coefficient of self-inductance. Now we have to find this L. We understood the process of self-inductance, but now we want to find this L value. Okay, so we say that this flux, I have not written flux over here. Flux basically is what? Magnetic field into area. Now what is magnetic field? U naught I by 2R. And area pi r square. Now flux actually in this one is proportional to what? Current. Remaining all the things are constant. Correct or not? Everything is constant. So we write here flux is proportional to I. And then we remove this proportionality. We write this as L into I. Phi equal to Li. And this L is the same coefficient of self-inductance. Now the question is, if I want to know L value, what shall I do? So L is equal to phi by I, what else? And what is phi? I have written over here. Mu naught I by 2R into pi r square. Mu naught I by 2R into pi r square. This is phi by I. So I gets cancelled. So L value that we are getting here is mu naught, and one R is also cancelled here. So mu naught pi r by 2. Okay, what is its unit? Its unit is Henry. Unit of L is Henry. Now dimensions again, can we find L's dimension? Obviously we can find it, right? What is it? Phi's unit is, or phi's dimension we can find with the help of magnetic field into area. In fact, we have found it already. So directly we can see it from here and put it. We'll be getting Henry's dimension. Shall we do it? Let's see. Where we have found the magnetic flux, and yes, here. Okay, to see that. This is here the dimensions. M t to the power minus 2 a to the power minus 1 L square. Okay, M t to the power minus 2 a to the power minus 1 L square. Right, so this one we are going to use. Where it is, okay, let's check. Okay, here. Right, so dimensions of phi, M t to the power minus 2 a to the power minus 1 L square. I hope I have written correct. Check it. Have I written correct? Huh? I have to see one more time. Come over here. M t to the power minus 2 a to the power minus 1 L square. Correct, I have written. Okay. So this is the dimensions of phi by I. So that means ampere is gone. No, why ampere is gone? Ampere is not gone. Okay. So unit of this is L equal to phi by I. That is M t to the power minus 2 a to the power minus 1 L square by I. That means ampere. So dimensions are M t to the power minus 2 a to the power minus 2 L square. Oh. So ampere is not cancelled. In fact, it has become a to the power minus 2. Okay. Okay. So this is the dimension of coefficient of self-inductance. But when we talk about coefficient of self-inductance, it is mainly used for solenoid. Inductor. Inductor is also solenoid. So we should find coefficient of self-inductance for solenoid first, not for this ring. But the concept is same. Concept is not going to change. Let's see. Here we are going to do, then we'll come back to mutual inductance. Okay. So self-inductance of solenoid. Self-inductance of solenoid. Okay. So what solenoid we are going to take? L length and its radius will take R, right? Okay. So okay, then we're going to make few turns in that one so that it looks like a solenoid. So like this. Okay, this is our solenoid. Making turns is also difficult. Let's take the help of this. Okay, like this. Okay, fine. Now, what we have for this one, its length is there. Length is L, not capital L. We have to make it small l here. And area, instead of area, let's take it as radius. So radius is r, small r. Okay. Now, what is flux first of all? Magnetic, and because of which current, which is in this one self inductance we are talking. So current is also in this these wires on. Current in these wires is going to produce magnetic field. What is that? Mu naught Ni. We know that. Okay. So flux is what? B into A. So here is mu naught Ni into A itself you can write, or if in this case we have taken radius, so pi r square we can write. And what is this N? N is number of turns per unit length. Remember that. So that way also we can write. Okay. Now I want to know what is its coefficient of self inductance. So coefficient of self inductance is what? Phi by I. So what will be getting? Mu naught N into pi r square. Mu naught N into pi r square is coefficient of self inductance of solenoid. Why it's required? Because we have to find out energy stored in inductor later on. Half Li square we did do in the first case I told you for the coil, and in the previous slide I told you what is the coefficient of self inductance for coil. Half Li square we did, right? Okay. Now we are talking about mutual inductance. Now mutual inductance means what? Mutual inductance, again we are going to take two coils because it's easy to understand from the coil. That's why we take coil. Okay. So we took one more coil, make it little smaller. Okay, like this. Or we can have it the same size also. Right. Now in this one what's happening? Current is here. And this current you are changing. You increase it or decrease it. Okay. So when you are increasing or decreasing, or if current is there in this coil, there is magnetic field, and magnetic field is also passing through this coil, okay, which is here. We'll make it little closer. Okay. So magnetic field produced by this coil is also passing through this coil. So what will happen? If you change this current, magnetic field through this is changing, which will produce self-inductance, we know. But that magnetic field is also changing through this coil. So because of this, in this also EMF is induced, and that's for mutual inductance. Okay, we call this as primary coil. We call this as secondary coil. Okay, so what the process is? Process is, if current through primary is changed, current through primary is changed, magnetic flux through secondary coil is changing. Through secondary coil is changing. Okay, due to this, EMF is induced. Due to this, EMF is induced in secondary. Is induced in secondary coil. Now that is mutual inductance. This is mutual inductance. Right. Okay, so let's do that. What to do? Now since it's very close to this coil. So we can say that the magnetic field through this one is also mu naught I by 2r only. What 2r? Let's see. This is radius. Okay, and now I want to find flux through this. So I'll write that as flux through secondary. Flux through secondary actually is what? Magnetic field of the primary. So magnetic field due to primary into area of secondary. Area of secondary, that means here also I want its radius. Okay, take its radius smaller. Okay, so magnetic field of primary is what? Mu naught I by 2r. Okay, so mu naught I by 2r. Okay, this is very small. Otherwise, we have to write mu naught I r square by 2r square plus x square to the power 3 by 2. That's also possible. It's not that it's not possible. Separation is considerable. We will write that. Okay. Okay, so mu naught I by 2r into area here is pi r square. Now, this is flux through secondary. Now, if I want to find coefficient of mutual inductance, then what it is? Same way like coefficient of self-inductance, here we can say pi through secondary is directly proportional to current through primary. Flux through secondary is directly proportional to current through primary. This I will change it, okay? I'll write it in some other color. Flux through secondary is proportional to current through primary. So, remove this proportionality and bring coefficient of mutual inductance. And this is mutual inductance. Okay, so M is equal to what? Pi secondary by I. Okay, so M is equal to phi by current in primary. This is current in primary. So, what we are going to get? Mu naught pi r square by 2r. That is the value of M. That is the value of M over here. Now, if suppose we want to do it for solenoid, so solenoid means two solenoids we require, then only we can do that. Okay, what we require is two solenoids. So, one solenoid you will be having the current, and because of that, flux will be changing in another solenoid. Okay, so this is mutual inductance. Alright, we will see a little more about mutual inductance before going into induced electric field. Let's see if we have anything. Yeah, here it is. Okay, there is a question in fact. Okay, we'll try and do this first. What they are asking us is find M. Now we know that what M is. Okay, M is equal to what? Flux through secondary by current through primary. Current through primary is given to us as I. And in this particular question, you see that this distance is given as X. So that means they are not very close to each other. I can't say that whatever is the magnetic field at the center of this coil, same will be here. I can't say. Okay, so then I have to find what is the magnetic field at its center, and we know the formula. So nothing new. Okay, flux through secondary we can write directly. So magnetic field produced by primary into area of secondary. What is magnetic field produced by primary? Mu naught I r square by r square plus x square to the power 3 by 2. Fine, we know that. Area of secondary pi r square. So mutual inductance, what it is? I will go, that's it. So mu naught r square into pi r square by r square plus x square to the power 3 by 2. That's all. What is unit of mutual inductance? Again Henry, no change. Okay, and dimension same as L. So no change in that. Now suppose in this over here only, if we try to do one for solenoid also, because solenoid only is called inductor. So let's do one question on that one. Do we have? Yeah, we'll take the place here only. Okay, or we'll go in the end. Okay, let's try to solve in the end. Here we'll solve. Okay. So let's make two solenoids, and how to make those? One inside the other one. Okay, one bigger one and then one smaller one. So one bigger one. Okay, and inside this one smaller one. Okay, fine. Inside this one smaller one of the same size. Right? Okay. All right. Then that will be challenging. Okay, fine. Smaller one. Okay. This is smaller one. All right. Just like this. Right then, make it solenoid now. So that means exercise we have to do. Smaller one first. Right. Okay. What is this? Okay. Making very less number of turns. Okay. Just symbolic these are. And here it is. That's all. Okay. Now in the upper one. Okay. Right. This is solenoid. Solenoid inside solenoid. Axis of the solenoid is common. Okay. Bigger solenoids radius you can say is capital R. Smaller ones radius you can say small r. Where is the current? Current is going in the upper one. Here is current. That's primary for us, and the inside solenoid is secondary. Okay. What do you want? M. What is M? Phi S by IP. What is phi S? Magnetic field of primary into area of secondary by current of primary. Magnetic field of primary, what is the magnetic field produced along the axis? So mu naught Ni, mu naught Ni. So mu naught N of primary into current. Okay, into what? Area of secondary, that is pi r square by I. That's it. So mu naught Np into pi r square. Number of turns in primary. Number of turns per unit length in primary into pi r square. This is mutual inductance. Okay, for solenoid. Right. Okay, let's move back. So where we were. Okay, we were talking about now induced electric field. What is induced electric field now? See, if suppose we say that there is magnetic field which is changing. Okay, maybe magnetic field is changing into this one. Why it's changing? That is not important at the moment. Magnetic field is changing. Okay, magnetic field is increasing or magnetic field is decreasing. So magnetic field is changing here. Okay, now what these are? These are loops we made. Are these rings? We can take them as a ring or we may not take them as a ring. Maybe hypothetical loops. So these are loops we have made. Now the question over here is, if the magnetic field is changing over here, can I say that EMF will induce in this coil, at least if suppose I assume this is a coil or this is a ring? because I can say that flux is changing through that. So EMF will induce in that. There's no doubt about that. Okay, true. Now, if suppose that this is also one of the coil, or maybe it's a loop. Does this area also belong to area of this one? Yes, why not? So can I say that through this second ring also flux is changing? Obviously. So will EMF induce in this also? Answer is yes. Yes. So will EMF induce in this larger one also? Yes. So EMF will be induced in all the loops as magnetic field is changing through common area. Changing through common area of these loops. Common area of these loops. Okay, fine. Now we have to talk about induced electric field, and we are saying that inside in this one there is EMF is induced. Okay, what will be the direction of EMF, what positive or negative, we'll see. But at the moment we are saying there is definitely EMF is induced in this one. Now EMF basically is what? Potential difference. EMF is what? Potential difference. EMF is potential difference. Okay, and if potential difference is there, that means electric field is there. Okay, we say no, electric field is always from higher potential to lower potential. So potential difference is there means electric field is there. Correct. So we have to find that electric field, induced electric field. So what is happening here? Just see. If here I am saying that magnetic field is increasing. Okay. So if magnetic field is increasing, in this one flux is increasing. And if flux is increasing, there will be induced current in that. And what induced current will try to do? It will try to decrease the increase in magnetic field. It will try to decrease the increase in magnetic field. Okay, so that means that induced current will try to produce its own magnetic field, which will be opposite to this one. Okay, I'm writing it. Now we have to find the direction of induced current also. So how to find direction? I'm just showing you that. Okay, here what's happening? Increase in magnetic field. Okay, change in flux will induce EMF and induce current through loop. Okay, current in loop. Induced current's direction is such that it opposes increase in magnetic field. Increase in magnetic field by producing its own magnetic field in opposite direction. Its own magnetic field in opposite direction. Opposite direction. Okay, now we know that this magnetic field is increasing. Where is this directed? Inside. So induced current will produce the magnetic field outside. So how should be magnetic field? Rather, induced current. Now, induced current can be clockwise or it can be anti-clockwise. So, if suppose we say it's clockwise. Clockwise means how it will produce the magnetic field? See, inside only. So, is it opposing? No. So then, how it will oppose? Like this. If it's like this, you see that magnetic field inside will be towards you, outside. Okay. So, induced current's direction will be how? It should be anti-clockwise. Okay. So, if anti-clockwise is the direction, how is the potential difference? We will say that here is a battery connected. Here there is a battery connected. Okay, so how is the battery? I say its positive end is here and negative end is here. So current will go like this because it moves from positive to negative only. So this is EMF. This is how EMF is. So if this is EMF, then how is electric field? Electric field is also along the current only. If this is IE and this is also E, because E is also from higher potential to lower potential. Okay, where is this potential difference? Within this wire. So electric field is also within this wire. So how is this electric field? This electric field is found in loop. Is it conservative electric field? No. Electrostatic field was conservative. This is non-conservative. Why? Because work done in this one, in moving a loop, is not zero, whereas in electrostatic field it was zero. In loop, work done by electrostatic force is zero because displacement is zero. Here it's not, because if electron is moving from here to here, it has done the work Q delta V. Electron is moving from here to here, it has done the work Q delta V, which is delta V is actually E here. Okay, so work done is QE. It's not zero, whereas in electrostatic field it was zero. So this electric field E induced is found in loops, whereas electrostatic field was not found in loops. Remember that. This is found in loops. E induces non-conservative. E induces non-conservative. Okay, sometimes the question reason assertion also they can ask you. Okay, so reason assertion they can come. So E induces non-conservative. How to find its value? Okay, now to find its value, what I'll do is I'll just one of the loop I'll be just removing. Okay, just remove one of the loop. Now we want to find its value. How to find? We know that EMF, which is potential difference, right? EMF is potential difference. That's delta V. And relation between delta V and electric field we know from electrostatics we know. What is that? Say electric field is minus dV by dr. Electric field is minus dV by dr. Okay. So this dV is actually electric, this EMF. Okay. So here we place. So I am going to write that E dot dr. E in place of dr I am going to write it as L. Okay. Here also we will write L only. I am not writing R. Okay. Leave it. I will do it later. E dl equal to what? dV minus E dl equal to E. E dot dl equal to E. Now E we can write in terms of flux also d phi by dt or anything like that. So this is how we can find electric field. Now this is what we saw then in Ampere's law, D dot dl. We said line integral of magnetic field. This is line integral of electric field, because here also electric field is tangential to this loop. Electric field is tangential to this loop. So that's why this is line integral of electric field, which is equal to EMF induced or rate of change of flux. Okay, so this is how induced electric field is produced due to change in magnetic field. Okay, all right. Right, there is a question on this now. Magnetic field is changing. You can see magnetic field is a function of time. That means magnetic field is increasing. Question is asking what is induced electric field at R less than R and R greater than R. R less than R means we will make a small one and we can put it inside here. Okay, and we will say this is R. Okay, and what we saw that so far in the previous slide, we said that actually E dot dl is equal to minus d phi by dt, right? Okay, Magnetic field is this, magnetic field only is changing. So area is what here? Here in this small one we have to find R is smaller than R, that means this R. So we'll write this as minus pi R square into dB by dt. Minus pi R square into dB by dt. E dot dl. E dl. dl means is the circumference. So circumference is what? 2 pi R equal to minus pi R square into dB by dt. Okay, what we can cancel? Pi and R gets cancelled. Pi and R gets cancelled. So E is equal minus R by 2 dB by dt. Now dB by dt we can write very easily here. What is it in this case? B naught. So minus R by 2 B naught. First question answer. Okay, second question. Now second question, what it says you, that second question, it says that you have got a bigger ring. R is greater than capital R. Okay, R is greater than capital R. Okay, let's make that one also. Okay, make one. Something like this, and we are bringing it over here. Okay, its radius I am going to consider as x. Let's find here. So is this area belonging to this also? We know that yes, it belongs to this, and magnetic flux is changing through this also. And formula is this. Okay, let's use it. Okay, so E dot dl equal to phi d phi by dt minus d phi by dt. Okay, so E into, now what is the circumference of this? This is 2 pi x, because we want to find in this what is the EMF induced or other electric field induced. Okay, so into 2 pi x here equal to minus area into dB by dt. Which area? Through which flux is changing. That means this area rho, not pi x square, pi r square. Okay, so pi r square into dB by dt. dB by dt will be what? V naught on. What you can cancel? Only pi. So here induced electric field is minus r square by 2x into V naught. Minus r square by 2x into V naught. So which area we have to take through which the flux is changing? In the previous case we took the smaller one, then why? Because through this one flux was changing. So that's why we took it. Pi r square we took. But here in this one, is the magnetic flux changing through this area? There is no. That's why you have to take that area only through which actually magnetic flux is changing. So that's why we have taken pi r square only and not pi x square. Okay. This is how induced electric field we find. This question anyhow we did. Now what is there? A solenoid has self-inductance L if its length is doubled, keeping number of turns constant. How self-inductance changes? Okay. The first thing is we should write what self-inductance is. What is its value? Okay. So L is what? Because I don't remember. So I will say it's phi by I. What is phi? Mu naught Ni into pi r square by I. So I got it as mu naught N into pi r square. What he says now? Its self-inductance is L. Okay, this is L, mu naught N into pi r square. If its length is doubled, keeping number of turns constant. So actually N basically is number of turns per unit length. So what I'll do is this small n I'm converting now. I'm writing this as N by L into pi r square. Write this N by small l. Okay, this I am writing as small. Now read the question again. It says that length is doubled, keeping number of turns constant. That means n is constant. Capital N is constant, whereas length is doubled. Okay. So L1 is mu naught n pi r square by 2L. So what has changed? L1 is L by 2. What else? Very simple. Your self inductance has become half. Okay. So we need to understand the question, then only we can solve. If we are going to see this is number of turns is constant and we consider this as small n is constant, then we'll write that nothing has happened. But he's not saying that. He says that length you are doubling, whereas number of turns you are keeping constant. That means capital N is kept constant, not small n. Okay, small n is in fact changed. Alright. Combination of inductors. Now so far we saw combination of capacitors, combination of resistors, now combination of inductors is also there. So combination of inductors again, series and parallel. So series, okay. So in series combination, this is how we make inductors. Inductors basically was solenoid. This is solenoid only. Okay. And here also something different. And they are connected in series with the battery. This is L1, this is L2. Okay. So here potential difference is V. What will happen? Through this one. Now L is there. Now L is going to work only when there is change in current. That's what we saw so far. Okay. Across them, potential will drop or EMF will induce only when there is change in current. Otherwise, no. So suppose there is change in current here. Let's say di by dt. So through this one also will be same change in current. Through this one also will be same change in current. They are in series. Okay. So across this there will be EMF induced, and across this also there will be EMF induced. Okay. And according to Kirchhoff's law, which law? Loop law. What loop law said? The sum of potential drop across all the elements in a closed loop is equal to 0. Okay. That means V must be equal to E1 plus E2, or V minus E1 minus E2 equal to 0. Right? So V equal to E1 plus E2. Now what is E1 and E2? I am writing directly here, no minus I am writing. Okay. So L1 di by dt plus L2 di by dt. Right? L1 di by dt plus L2 di by dt. That is equal to what? Combinations self inductance. So L effective into di by dt. What is L effective meaning? Meaning is if in place of these two, we are going to have a single inductor which can behave in the same way as these two together, then its inductance is L effective. Okay. So what we can see, it's in series connection, so this di by dt gets cancelled. So L effective is equal to L1 plus L. Very similar to resistance. Series connection, we are getting L1 plus L2. Okay. Then parallel connection. Parallel, what's going to happen? We see parallel. In parallel connection, what happens? Potential remains same. Potential difference remains same, right? Okay, so in this one also two inductors we'll take. This is one, this is another one. Okay, two different types, and they are connected with a battery. This is V, this is L1, this is L. So through this I current goes, here goes change in current, let's say di1 by dt, and here goes di2 by dt. So net change in current di by dt we can write as what? According to junction law, di by dt is equal to di1 by dt plus di2 by dt. Simple, right? Okay. Now what will happen when this current will go across this? There will be EMF induced, that will be E2, and here will be E1. E2 is what? E2 actually is L2 di2 by dt, and this is E1. This is L1 di1 by dt. How this came? We didn't talk about EMF, no, in that one. Did we talk about EMF in self-inductance? I think no, we didn't talk. Only we talked about flux. Yes. So far we talked about flux. Okay. We'll discuss it. Okay. Here also I have written L into di by dt. So flux we discussed. Flux was L into I. So d phi by dt will be what? EMF. EMF will be what? L di by dt. Because current only is changing. L is not changing. L is constant. So d phi by dt, which is EMF induced, is equal to L di by dt. Okay, and even in mutual inductance also, d phi by dt will be M dip by dt. And mutual inductance also, what will happen? In that one, what we write? Phi through secondary is equal to M into I through primary. So phi through secondary, that means d phi s by dt, that is EMF induced in secondary, will be equal to M into dip by dt. And minus sign is always there. Okay, because opposition is there. Okay. All right, so here we are using it. E2 equal to L2 di2 by dt, E1 equal to L1 di1 by dt. So let's put it here. di1 by dt value is E1 by L1, and this is E2 by L2. Now what we know, E2 is basically the potential difference across this, and E1 is potential difference across this. But since they are in parallel, potential difference across this inductor and this is same, and that is equal to, okay. So what we can do? We can write this as actually V by L1 plus V by L2, and this di by dt I can write as V by L effective. So what we are getting? 1 by L effective equal to 1 by L1 plus 1 by L2. Exactly similar to resistances in parallel. Okay, the direct question can come, so you should be remembering it so that we can solve it. Direct question means either they can ask you EMF induced or they can ask you the net self-inductance. Okay, so we should remember this. Okay, then what is there? Then one more thing is there, the relation between coefficient of mutual inductance and self-inductance. There is a relation between them. Okay, what relation? Okay, okay, relation between coefficient of, I think it should be there on slide. Let me check. No. Okay. Relation between coefficient of mutual inductance and self-inductance. Okay, there is some relation between the two. When two coils are kept very close to each other, and we know that mutual inductance is also happening, and we know that when mutual inductance is happening, self-inductance is also there. Okay, so what relations they have? If we say, suppose I am explaining you through the coil first. Okay, two coils are there. This is one coil, this is another coil, and we can have it slightly smaller one. Okay, like this are they, and they are so close to each other that whatever is the magnetic field at its center, same is the magnetic field at its center also. So here let's say IP, current in primary. Okay, this is here like this. So magnetic field is same through this as well as through this. Its radius is R and its radius small r. Right. So what happens? This is going to produce its own magnetic field. What will be the direction? We know how to find the direction. Current you can see at the top is inside. Okay. The top is inside. So where is the magnetic field? Is towards left. So here also magnetic field I will say is B, and here also magnetic field is B. Same magnetic field. They are very close to each other. Okay. Magnetic field through center of both coils. Through center of both coils is same. Is same. Okay. Correct. So we know that how to find coefficient of mutual inductance between these two. Now the thing is like if coefficient of mutual inductance because of this larger one through this one, when I am going to consider this as secondary. Okay. So coefficient of mutual inductance due to first one for the second one. Okay. So mutual inductance of secondary due to primary coil. What it will be? Flux through secondary by current through primary. So flux through secondary is magnetic field produced by primary into area of secondary by current through primary. Okay, clear? MSP, mutual fund of secondary due to primary. Okay, this will be equal to mutual inductance of primary due to secondary as well. That means if instead of IP we are having here IS, in this one we are going to have IS. This produces magnetic field over here. Same magnetic field is through this one. And we are going to find mutual inductance of primary through secondary. It will come out to be same. That means always remember MSP will be equal to MPS. Okay. This is proved. First of all, we proved through measurements. Okay. When you are doing the experiments, you proved it. And then through the theory also it was established. They said that there is a theorem which proves it. This theorem is called theorem of reciprocity. Reciprocity. Okay. So one relation is that whether you are talking about mutual inductance of secondary due to primary or you are talking about mutual inductance of primary due to secondary, both are equal. Point number one. This is important for us. Second thing is, because we wanted to have the relation between mutual inductance and self-inductance. Then self-inductance of this we can say is L1 and self-inductance of this we can say is L2. Then when the magnetic field, as we have written that center of both the coils is same magnetic field, then remember that the relation here is M square equal to L1 L2. What is M square meaning? You know, this into this. This into this is equal to actually L1 into L2. This also can be proved, but there is no time. Right now we will remember that. Okay. M square equal to L1 L2 or M equal to root L1 L2. This is the maximum value of coefficient of mutual inductance. Maximum. M max is equal to root L1 L2. Okay. Now, whether M is going to be maximum or M is going to be minimum, how to define or how to find? As I told you that if the magnetic field through this one and this one is same, then M is this. But if suppose that we are going to have certain distance, then what will happen? Magnetic field through this one will be different and magnetic field through this one will be different. Then M will be little less than root L1 L2. Okay. So how to define it? We write this as like this. M is equal to K root L1 L2. What is this K? K is called coefficient of coupling. Coefficient of coupling. Okay, maximum value of K is 1, right? So K is less or equal to 1. K is less or equal to 1. Okay, remember that. So coefficient of coupling, they can ask you sometimes, they will give you L1 value, L2 value and M value. And they will say you what is the value of coefficient of coupling. So we can find K is equal to M by root L1 L2. Correct? Right. Okay. Then sometimes it happens that you connect the inductors in such a way in which mutual inductance also is taken into account. What is the meaning of that? Like we connected in series connection. Okay. Now these two are close to each other. Okay. So its coefficient of self-inductance is L1 and coefficient of mutual inductance is M1. This is L2 and this is M2. Now, what is going to be the net inductance here? Okay, so self-inductance you already know, it will be L1 plus L2. They are in series. You know that. But what about M1 and M2? And M1 is what? Now, M1 is when there is change in current through this one is happening. Okay, so in this one, mutual inductance was there. And when there is a change in current here, here mutual inductance is happening. Okay, so in this case, what will be effective value of L? It will be L1 plus L2 plus M1 plus M2. But M1 and M2 used to be same only, right? So you can write as 2M. M1 equal to M2 equal to M. So L1 plus L2 plus, just remember that. Okay. If in series only, it comes out to be like this. They are not parallel, okay? Same current is going. They are not parallel. They are series only. Here is L1, M1, L2, M2. In this case, what is the net effective coefficient of inductance? Then in this case, it is L1 plus L2 minus M1 plus M2. Why? Because direction has changed. Okay. And because of that, direction of magnetic field will change. That's why mutual inductance is happening in opposite direction to self-inductance. Okay. Self-inductance here going to oppose the current, change in current, but mutual inductance is going to add it. Because here direction is different. Because of this direction only magnetic field will be producing here, no? Okay. So because it's happening in opposite direction there is increase in magnetic field. So what it will do? It will try to produce its own magnetic field in this direction. Whereas L1 is trying to decrease. So both are in opposite direction. So it becomes L1 plus L2 minus 2M. Remember that. Okay. So this is the relation between coefficient of self-inductance and mutual inductance, and then when you are connecting them, this is how the effective value is, right? Okay, let's go back. Okay, where are we? Motional EMF. Yes. So we are here at motional EMF. Now, motional EMF is what? If there is one conductor is moving in magnetic field, then EMF is induced across it. This is a conductor. Okay, this conductor is moving, let's say with velocity. And magnetic field B. And its length is L. Then EMF is induced across it. How much is EMF induced across this one? I'm writing directly, okay. But actually what happens that the theory I'll explain you. This is being a conductor is having free electrons on its surface. So when this moves with velocity v, okay. So electrons also we can say are moving with velocity v in this direction. So electrons when moves in magnetic field, they are subjected to a force q v cross v, and because of that electrons will start moving downwards. Electrons will start moving downwards. You can see that how we used to find the force q v cross v, that means v cross v. So v is this, like this, v is inside. So where is the force? Upwards. Okay, upwards is the force on positive charge. Here is negative, so minus q v cross v. So that means electrons will come down. So all the electrons will come down, this end will become negative. So this end will become positive. So how much will be the potential difference finally? When all the electrons which were supposed to come over here, okay, have come downwards and there is no more electron's motion is there downwards. Okay, then we will say that equilibrium has reached. And in equilibrium, we say magnetic force on electron is equal to electric force on electrons. Why electric force? Because there is a potential difference here, and that's what we are saying is EMF. Okay, so here is potential difference, delta V. So electrons here will be subjected to electrostatic force, which will be E into E, and here will be magnetic force, which will be E V cross B. Both become equal. So if they are equal, we are getting EMF or delta V. EMF or delta V is equal to what? You can see that E and E gets cancelled. Correct or not? So first of all, we are getting E value, capital E. Capital E means electric field. So electric field we are getting as VV. Now remember here V should be perpendicular to magnetic field. Then only VB I can write. Otherwise I can't write. Okay. Now E is given. E we got. E is what? Minus dV by dr. Minus dV by dl. Okay. So dV for EMF is equal to what? VB dl, or you can write in terms of vector if you want to write V cross B dot dl. This is EMF. Or in general terms, we write it as VBL or VBL. Now this minus is not required here because we already have this is positive, this is negative. We can find it very easily, right? With how, always remember, do it for positive charge. So velocity is like this, okay. Magnetic field inside. So where is positive charge going? Upwards. So this is positive, this is negative. So EMF is produced if there is a conductor which is moving in magnetic field, and its magnitude is BVL. B and V are perpendicular to each other, and L is also perpendicular to all of them. You can see that V is along x-axis, magnetic field is along z-axis, and L is along y-axis. All are perpendicular to each other. If any one is parallel, if B is parallel to V, EMF 0. If B is parallel to L, E is 0. If V is parallel to L, E is 0. Remember that. All are perpendicular. If there is some angle given, then take the perpendicular and write. Take the perpendicular and write. Okay, suppose that V is given, it's inclined like this. So we'll take its V cos theta, V sin theta. And V sin theta is not producing any EMF. V cos theta will produce. Like that we have to take components. Okay. So this is motional EMF due to straight line motion of the conductor. Let's see question here. This is semicircular wire which is moving with velocity v upwards in a magnetic field which is along z-axis. Okay, how much is EMF induced between AB? What is the formula for EMF? EMF formula is VVL. And what is L? What is L? L is effective length between two ends about which you are asking the EMF. So here what it is? AB. What is effective length? Is it vector over here? Yes, it's a vector. So vector always means is displacement. Okay, it's always displacement vector. So we are not going to take this pi r. I am going to take as 2r. So EMF here is going to be VV into 2r. That's all. Finished. VV into 2r volt. Okay, that one. This is a ring, and I want to find potential difference between AB or EMF between AB. So what I'll do is, I'll make it like this. Okay. For upper ring, this one, and for lower ring, this one. So for upper ring, I already got VV into 2R. But this time what I'll do, I'll try to find out that which end is positive and which end is negative. So here you see that velocity is where? Upwards. Magnetic field is inside. So velocity upwards, my hand is like this. Okay. Towards magnetic field, I curled it. So where is my thumb? So positive charge will move towards left. So that means this is positive, this is negative. This is positive, this is negative. Right? So how will I make? I'll make it something like this. EMF. So same thing I'll do here. E. Now look at the lower one, lower side. Now what's happening in this case? Now in this case, this is also going upwards only. It's also going upwards, the same velocity. Then in this also same EMF will be producing. Yes. Same way, this is positive, this is negative. Yes. So here also E. Now what is net? If you go it like this, you will find that net EMF is 0. According to Kirchhoff's law, see. It's like this. So if I ask you what is the net EMF here in this one, you will say 0. How much is current in this one? You will say 0. See that? If we start moving from here like this, so when you move from here, you are going from higher potential to lower potential, right? Minus. Then you'll come over here. Here you are moving from lower potential to higher potential, right? Plus equal to 0. 0 only, na? What is the net EMF in this closed loop? 0. The net EMF 0. Or in other way, I could have said that in this one, if see the displacement of current is 0, no? From A, you are coming back to A. Where is B in this? In fact, B I should not write here. Okay. And there is no B. What is the net EMF in this one? 0. Okay. Because displacement is 0. From where to where it's going. Alright. So net displacement there is 0. So because of that, we have written EMF induced is 0. Whereas here, displacement is from A to B. So we are able to write. Clear? Okay. This is motional EMF. Now, there is one more motional EMF because of rotation. Okay. Motional EMF due to rotation. Due to rotation. Okay. But is the formula different here? No, same formula. BVL only. But in this one, problem is because it's rotating like this and this end is here fixed. This end is not going to go. So this all is rotating. So because of this one, every segment is having different velocity. If I say this is x, then its velocity is x omega and its velocity is L omega. So every segment is moving with a different velocities. So then how to find EMF? We have to add EMF of all, that means integration we have to do. Okay, so we'll do integration. This radius x we have taken. So this small segment's length we will take as dx and then we are going to write BVL only. Okay, so we'll write dE equal to B into x omega into L is dx and then we are going to integrate. From where to where we will integrate? From here to here, 0 to L. So we are getting what? B omega x square by 2 and this becomes B omega L square by 2. Okay, this is EMF induced or potential difference. Which end is positive, which end is negative? Again very simple. In this one, velocity of the charge is where? Downwards and magnetic field is where? Inside. So downwards making is tough, like this is downwards, right? This is downwards and magnetic field is inside. Right. So where is the positive end? This end is positive. That means this end is positive here and this end is negative. This end is positive, this end is negative, velocity is downwards, magnetic field is inside. You can see that where is positive charge going. Okay, so EMF is V omega L square by 2. Simple. You can remember this formula, well and good. Or otherwise, remember BVL only and derive it. So, better remember that. Okay. Let's see question on this one now. What is it? We have to find potential difference between B and C. Simple question. Okay, what you'll do is, first find potential difference at C with respect to this. That means find EMF in entire rod. Then you find EMF in half of the rod. And then put it in that one, you will be getting it. Which end is positive? Always remember these ends are positive. What I am finding, if this is O, I am actually finding VC minus VO. And what is that? B omega L square by 2. Little while ago, I found positive, negative. So this is higher potential, this is lower potential. So EMF is this. Same way for this one, if I have to find VB minus VO, what will come? B omega L by 2 whole square by 2. So this will be what? B omega L square by 8. I'll put it in this one. VB minus VC means what? VB minus VC means VB minus VO minus VC minus VO. VO gone. So VB minus VC is what? This says B omega L square by 8 minus B omega L square by 2. Okay, what's going to come? I think 3 B omega L square by 8 will come. 8 B omega L square minus 4 B omega L square. So minus 3 by 8 B omega L square. So that means potential at C is more than potential at B. Okay. All right. Okay. Then here only I'll give you another question, or we'll go into the empty one. Now suppose I have one disk. This is a disk, solid. The solid disk. Okay. And it's moving ahead. Okay. It's moving ahead. Should not do like that. Okay. This moving ahead I'll just remove. Okay. Then what I want it to rotate, not move in a linear way. I want it to rotate with omega. Radius is r. So it's rotating. Okay, and there is magnetic field. In magnetic field, it's rotating. So magnetic field is also here. There is magnetic field like this. Now the question is, how much is EMF induced across the periphery and the center? Okay, EMF between circumference and center. Okay, EMF between circumference and center. So what is in this one basically? There are infinite wires. These are there. These are wires because it's solid. Okay, these are all wires here. Like this. So what you'll do, across one I will find how much is the EMF. And then I'll connect parallelly because both are connected between circumference and center only. All, not both. All are connected between them. So there are infinite batteries in fact here, connected parallelly. Okay. So EMF between one we are finding. So what I have given you omega, what is the radius r? So EMF simply I can write now B omega r square by 2. What is the problem with that? Okay. Which end is positive, which end is negative can we find? Yes, we can find, why not? So we can see that we can take any point here, suppose this. So its velocity in this way. Velocity is like this. Where is magnetic field? Inside. So you can see that where is my thumb? Okay, so this end is positive. So that means circumference is positive. Circumference is positive. And center is negative. That means center is at lower potential. So now how many batteries are connected whose EMF is this? Infinite. So if parallelly they are connected, we know if they are connected parallelly like this, net EMF will be what? Net EMF will be E only. We have seen that in current electricity. Okay, net EMF is E. So total answer is also this only. This is EMF across every single spoke of this disk. Okay, and that is also the EMF across circumference and the center. Clear? E is B omega r square by 2. Remember that. Okay. Sometimes this is also asked from you which end is positive, which end is negative, which end is higher potential, which end is lower potential. So you should be able to find it. Okay. All right. Let's move back. So where are we? We are here. Okay. Here we were. Okay. Let's go to next. Next is another question is there. What is this question? Let's see. This question says magnetic field is given in vector form, this much Tesla. A rod of length 1 meter placed along y-axis moved along x-axis with velocity 10. What is induced EMF? Very simple, but all the things we have to take in vector form and find EMF. Vector form means minus V cross B dot length. Okay. So minus V is what? 10 I cap along x-axis. Okay. B is what? B is this. 3I plus 4J plus 5. Then dot length is along y-axis. So J cap. Okay. So here when I'm going to multiply the cross product, I with I is gone, 0. So what we are getting over here, this minus is here. I cross J is K. So 10 into 4, 40 K cap. Okay, then I cross K is minus J. I cross K is minus J. So 10 into 5. So minus 50 and J cap. Dot J cap. So here is dot. So K dot J 0. J dot J 1. So minus 50 minus and minus plus. So plus 50 volt is your answer. I hope I have done it correct. I cross K is minus J, correct? 10 into 5, yeah. Okay, so plus 50 volt is our answer. So this way we can find if the things are given in vector form. V cross B dot dl. Remember the formula. Okay. Okay, one more question is there. Magnetic field is into the board and you have this as this one. Okay, this one will make frame. Okay, this is moving. This is basically a conductor which is moving with velocity v in a magnetic field B, and we have to find EMF induced across this, not across this, across AB only, not across full length. And length of this AB section also not given. So we can find with this triangle is given over here, 60 degrees given. Okay, easy then. Okay, because only length we have to find. Magnetic field and velocity anyhow are perpendicular to each other. This is z-axis, this is y-axis, x-axis, and length is along y-axis. So everyone is perpendicular. We don't have to bother about anything. Okay, we have to just find the length of this one. So this is L. Now this is 60, so this is 30 for sure. So this is L sine 30, and this also L sine 30. So very easy now. So EAB is B is here, V is here, and length is 2L sine 30. That means L only. The answer is BV here. Answer is BV here. Very simple. Okay. Then the last topic here. Energy stored in inductor. We already discussed half Li square. So energy stored in inductor is half Li square. When will this be energy? This is the maximum energy stored inside inductor. Half Li square. Okay. The maximum energy. When current in the inductor is maximum. When current in inductor is maximum. Okay. When current in inductor is maximum. Alright. Then you also have in this one energy density. That means energy stored per unit volume. Energy stored per unit volume. per unit volume. Same thing is there in capacitor also, energy stored per unit volume, which is energy density. So here this energy density is V square by 2 mu naught. For inductor we are talking, what is magnetic field inside inductor? Mu naught Ni, we all know that. So mu naught Ni by mu naught Ni whole square by 2 mu naught. That is the energy stored per unit volume. We have to remember, yes, energy density we should be remembering. Same way in capacitor. In capacitor, the same energy density formula was half epsilon naught E square, where E is electric field strength, here B is magnetic field strength. Okay, energy stored is half Li square, in capacitor it was half CV square. Capacitor opposes the change in voltage fluctuation, it opposes the fluctuation in voltage. Inductor opposes the change in current. Okay, remember that point also I am writing here. Inductor, because self-inductance too. So self-inductance means what it is opposing? Change in current. Okay. So inductor opposes change in current. Change in current. Whereas capacitor opposes fluctuation in voltage. Change in voltage. So that's why both are connected together in any circuit. Both are safety devices that you'll understand in AC. One is called low pass filter, other one is called high pass filter. So both are necessary in the circuit to safeguard all the appliances. Okay, so this is half Li square. Right. Now certain questions of capacitor and inductor. Shall I give you? Okay, let's do one question. Okay, one question will solve. Question is like this. Okay. One inductor is here and one capacitor is here. Okay, its capacitance is C and initial potential in this one is V1. Initial means is let's have a key over here. Okay, there's a key over here, initial. This is L. Initially, capacitor is charged to potential V1. Okay, when key is closed, after some time, potential across capacitor is V2. Across capacitor is V2. Find current through inductor. Find current through inductor. That's the question. Okay, if you understand the question, it's very easy. What is easy in this one? Easy is energy is conserved. Energy is only going to dissipate across resistor. Across these two, energy is not going to dissipate. Unless, normal thing is there any possibility of having an inductor without resistor? Answer is no. Inductor is what basically? You have made coils out of one conductor only, no? So conductor definitely has resistance. So it's not possible to have an inductor which doesn't have resistance. No way. That is also one of the questions. Okay, I'll frame that one and then we'll come on this one. Okay. So your question is it possible for an inductor to be resistance-less? Okay, answer is no. Answer is no. Then in the previous question that I was taking, here resistance is there or not? No. Why? Because in these questions when we solve it, we take is ideal. Okay, these are ideal. This is ideal. Unless they mention, they will mention it. If resistance is there, they will connect a resistance. Or they will say L and its resistance is R. Okay. I think one of the question, okay, we'll solve one more question in that one. Okay, in which I will show you resistance is given along with resistance. Okay. Inductance and resistance both are given together and we'll solve that question. Right. So let's see first this one. Right. So is it possible for an inductor to be resistance-less practically? Answer is no. Then another question comes out. Is it possible to have a resistance without inductance? Is it possible for a resistance to not have an inductance? Answer is yes. This is possible. Okay, this is possible. Its answer is yes. So inductor is not possible to be without resistance, but resistance is possible without inductance. Okay, let's go back. So here this is ideal and doesn't have resistance. So if it doesn't have resistance means energy is not dissipating. Energy is not dissipating means energy is conserved. So whatever energy is lost by this capacitor, that energy is going in inductor. What is initial energy? Half C V1 square. Okay, initial energy is what? Half C V1 square. Initial energy. U I am writing, then you will consider it as potential energy, right? Energy initial. Half C V1 square. Because only capacitor was having. Energy final. Now energy final is in both. Half C V2 square plus half L I square. Equate both. We'll get I value. Simple question. If you understand, simple. If you don't understand, that's all. Okay. Then what I was saying that I will tell you one question I will do. Okay. One question we will do in which I will give you resistance also along with inductor. So suppose question is like this. Here is an inductor. Okay. It's connected across a battery. Its inductance is, let's say, 2 Henry and resistance is 20 ohm. And this is 100 volt. Question is asked from you, find maximum energy stored in inductor. Maximum energy stored in inductor. Now in this one you see that I did not make resistance separately. I directly written that R is there inside. Or I could have done it in different way also, slightly. This is your inductor and along with that I would have made resistance. Like this. That's also fine. 20 Henry, sorry, not 20 Henry, 2 Henry. Yeah. 2 Henry and this is 20 ohm. Same question I could have given you like this. Both have same answer. Both are same. Okay, so find maximum energy what? So we have to find what is maximum current. What is maximum current in that? 5 ampere. I is equal to what? Potential difference delta V by R. Delta V by R. Okay, maximum current when it says that means the opposition of inductor has become 0. When you are talking about maximum current, there is no opposition at that time because current has become maximum, that means there is no fluctuation, no increase in current, no decrease in current is happening. So when that is happening, current maximum is delta V by R. Delta V is what? 100. 100 by 20. That's 5 ampere. Then energy stored is what? Half Li square. So So 1 by 2 into 2 into 5 square, 25 joule. That's it. Okay. So that's it for EMI also. EMI is over. If you go through all this, okay, this will give you enough confidence that you can solve almost all the questions that are going to be asked in. You don't have to go beyond this. That's enough. Okay. So scan the QR code. Okay. Tomorrow we are starting AC and we'll try to finish it tomorrow itself. Time is less, so we'll try to finish your syllabus as early as possible. One big topic is, other than AC will finish tomorrow. So other than that, only one big topic is there, and that's ray optics. It will take a little more time. But all other topics are very small topics, so we can finish them. Okay. So scan it now, and tomorrow we are starting with AC. Okay. Completed, students?
Yes, sir.
All right.